All right, so this will be the last video for this section. We're going to look at a couple of examples here. First of all, this one, we're given a vector field and a couple of curves in the plane here. So this is going to be, we're thinking of this in terms of a line integral over plane curves. And we're not given an expression for the vector field. But what we're asked to do is determine that if we were to take the line integral over either of these two curves, C1 or C2, in this vector field, will the solution come out to be positive, negative, or zero? And thinking about how we derived the line integral over a vector field, or of a vector field here in the previous video, what this comes down to is the dot product of these two vectors. Remember, the line integral is defined to be f dot t ds, where, the integrand in a line integral is f dot t. The dot product of f and t in this picture would be positive. And the reason I know that is because these two vectors are acute. If you remember, the dot product of two vectors can be evaluated in one of two different ways. You can either do the component-wise multiplication, or it's the product of the magnitudes of these two vectors times the cosine of the angle between them. Because of that, if these two vectors are acute, the cosine of the angle between them will be positive. If these two, I think I said if these two vectors form an angle that's acute, the cosine will be positive, meaning the dot product will be positive. If the angle between the two vectors is obtuse, then the cosine of that angle would be negative, making their dot product negative. So really what it comes down to is thinking about the tangent vectors, the unit tangent vectors along this curve, and the vector field and the vectors that it displays, how they cross that curve, whether it's done at an acute angle or an obtuse angle. Hope I explained that well. So let's look at this example right here. Starting with C1, that's this curve right here. Okay, the curve, its orientation is pointing this direction. So when we evaluate the unit tangent vectors, we're going in the direction of that orientation. It would be traveling that direction. Now, if you notice, this blue vector here from my vector field and this unit tangent vector appear to be acute. And in fact, if I continued drawing in unit tangent vectors along this curve, it appears that, at least from the parts of the vector field that I can see, these blue vectors here, they all seem to form acute angles with those tangent vectors. So that means that the integral along C1 of my vector field, f dot t ds, we would expect that to be positive. Again, because we have a bunch of acute angles formed between the vector field and the unit tangent vectors. Notice also that if I were to have reversed the direction, the orientation, if we were to traverse C1 this direction, then the unit tangent vectors would be pointing the opposite direction, forming obtuse angles instead of acute angles. So if I took the reverse orientation of C1, we would expect this to be negative, and that's part of the intuition that we've already talked about. When you reverse the orientation of a curve, you get the opposite of the original integral. Now, in the case of scalar fields, when we integrated with respect to arc length, that didn't happen. But in this case, we can see that would in fact happen. Let's think about the second curve there, f dot t ds. If I were to integrate over the curve C2, let's look at the direction or the orientation of this curve and think about how that compares to the vector field. Well, at least in this case, it appears that the angle between this blue vector in the vector field and the corresponding unit tangent vector would be obtuse. So if you were to draw other points, you would see that that appears to be the case everywhere else along that curve as well. So we would expect this to be negative. Okay. Let's move on to this last example. This one we do have a function that we want to work with, a vector field, and we're given the parameterization for a curve C. This corresponds to the curve C here. So we're going to use the we're going to evaluate f dot dr, and we know from that what we need are a couple of things. First of all, I need f of r of t. How do I evaluate f of r of t? Well, here's my function f, and here's r of t. This is the x. I think of this as the x, y, and the z. It's the I, j, and k components. So plugging in t squared anywhere I see an x up here, t cubed anywhere I see a y, and negative 2t anywhere I see a z, gives me f of r of t. So let's see what that looks like. T squared, I have x plus y squared. So y squared would be t to the sixth, and I'm adding t squared to that. So that'd be t squared plus t to the sixth I. And then here, xz, so that would be t squared times negative 2t. That would be minus 2t cubed, and that's the j component. And then y plus z is going to look like t squared minus 2t. So plus t squared minus 2t. That would be my k component. Okay. Now, my r prime, remember we're going to need that as well for the dr in our line integral. So I'm going to r, which is given to me here, and I'm just taking its derivative. That becomes 2ti plus 3t squared j minus 2k. Okay. Now, how do we find f dot dr? Well, that's the dot product of these two vectors, these two vector functions. So I'm dotting this guy with this guy. T squared plus t to the sixth times 2t. That's going to be 2t cubed plus 2t to the seventh plus the product of the next set of components, the j components. That's going to be actually negative, so it's minus 6t to the fifth. I could see that's what the product of these would be. And then negative 2 times this. It's going to give me minus 2t squared plus 4t. That's what my dot product comes out to. There's some simplifying that can be done here. This is equal to 2t to the seventh minus 6t to the fifth plus 4t. Okay, so now to wrap it up, if I want the line integral of f dot dr, that would be equal to the definite integral. The limits of integration come from my parametrization here, so that's 0 to 2. And then this is 2t to the seventh minus 6t to the fifth plus 4t dt. Okay, and again, polynomial, really easy to integrate that, so I'm going to skip the lengthy work. That one comes out to 8. Okay, so you're going to notice pretty much all of these problems come down to figuring out what your ingredients are. In this case, I need f, and I need f of r of t and r prime of t, and then I take their dot product. That's what f dot dr is. Okay. All right, very last thing for this video is to establish a connection between our line integral over a vector field, or line integral of a vector field, and the line integrals that we talked about where we integrate with respect to x, y, and z. So it may seem a little weird that we initially defined the line integral when it came to scalar fields with respect to arc length, and then we just kind of said, hey, we could also take line integrals of this form where we integrate with respect to x, y, or z, and we didn't really give any motivation for why we do that. Well, the reason is because there's a direct connection between what we just talked about and those types of integrals. Let's look at this. If I want to do the line integral of f dot dr over this curve C, but from the work that we did previously, we said that this is equivalent to this. However, r of t, if I'm notating r of t, or if r of t is this, r of t equals x of t I plus y of t j plus z of t k, then that's the same thing as r prime of t then would be this, x prime of t plus y prime of t plus z prime of t. F, our function f, we define in terms of pi plus qj plus rk, but each of these, p, q, and r, are each functions of 3 variables. And just to refer back to the previous example, that's like what we saw here. This would be p, q, and r. You notice each one of them is a function of x, y, and z. So plugging r of t into f is like plugging x of t, y of t, z of t into p, q, and r, giving me this really long, messy kind of computation here. However, once we take this dot product, you notice what we have. We have p with the parameterization x prime plus q y prime plus r z prime with this dt. That is integrating with respect to x, y, and z. So this can be written more compactly this way. And this shows that the line integral of f dot dr over the curve C is equal to the line integral over C of p dx, q dy, r dz, where each of these is a multivariable function that show up as components in this vector field. That's what this is saying right here. Okay, so that connection is going to be really, really important in the work that we do in later sections, but that's going to wrap up 16.2.